Hello, I'm Huang. The paper I'm going to present today is Timing-Aware End-to-End Circuit Compilation Framework for Modular Quantum System. This work is done by me and my advisor, Wiki Max. So unfortunately, my flight was canceled, so I couldn't make it to German. But I'm really glad to present my work here, and many thanks to the OC for allowing me to report it online. Sorry. Okay, so current quantum processing units, QPU, lacks sufficient qubits to tackle real-world problems. However, scaling an individual QPU to accommodate more qubits faces significant fabrication challenges, like congestion in qubit control wiring and increased crosstalks. So, to overcome these limitations, the integration of multiple QPUs into an interconnected quantum system is adopted. By connecting individual QPUs through communication links, quantum system can scale beyond the constraint of monolithic architectures. And to execute a quantum circuit on a modular quantum system, it's necessary to perform compilation, which mainly consists of two stages, qubit placement and qubit routing. In the placement stage, each logical qubit in the circuit is mapped to a physical qubit in a quantum system. And in the routing stage, inter and intra QPU operations are inserted to execute all the gates in the circuit. Okay, a modular quantum system consists of multiple interconnected QPUs. So for example, in the figure A, the system here consists of two QPUs, D1 and D2. The QPU in the system are connected via communication links, like the green lights here in figure A. And each communication link links a pair of physical qubits from two different QPUs. And the linked qubits in figure A serve as communication physical qubits. And the remaining qubits, the blue ones, they are data qubits. And here are the operations we used in the routing stage. To move qubits within a QPU, we can use a swap operation to exchange the locations of two qubits. Like in figure A, after applying a swap, the locations of Q1 and Q2 are exchanged. We use a tailored data operation to move a logical qubit from one QPU to another QPU via a communication link. So in figure B, Q1 is transferred from QPU1 to QPU2 through a tailored data operation. And instead of moving a qubit across QPUs, we can also emulate the execution of a two-qubit gate between qubits on different QPUs using a tailored gate operation in figure C. We emulate a CZ gate between Q1 and Q2 with a tailored gate through the upper communication link. Here is the problem formulation for circuit compilation problem on modular quantum systems. The input is a quantum system and a logical circuit, and the output is a functionally equivalent physical circuit that can be executed on the system. And our objective is to minimize the physical circuit latency. In this work, we assume an as soon as possible execution model, where each gate in the physical circuit is scheduled to begin as soon as all of its operand qubits are ready. Then the finish time of each gate and the latency of the physical circuit is defined as below, like here. And in our framework, there are two main stages, placement and routing. In the placement stage, each logical qubit in the logical circuit is first assigned to a QPU in the given modular quantum system. And then we map each logical qubit to a data qubit within that QPU. In the routing stage, we iteratively select a Taylor data or Taylor gates for insertion, and then we insert multiple swap operations to execute the gates that do not require any additional Taylor data or Taylor gate. Okay, let me introduce the placement stage first. In this stage, we propose a dependency and interaction-aware assignment method to assign logical qubits to QPUs, taking into account both the execution order of two qubit gates and the frequency of qubit interactions. We iterate through the two qubit gates according to the topological ordering. For each two qubit gates, Qi and Qj. If Qi has already been assigned and Qj has not, then Qj is assigned to the QPU that is closest to the one holding Qi and can still accommodate Qj. If neither Qi nor Qj are assigned, then we assign them to a QPU, Dn, that can still accommodate Qi and Qj and minimize the cost defined here. So, the logical qubits that interact early in a circuit and frequently with each other, they will be assigned to nearby QPUs. Subsequently, we leverage a dynamic look-ahead heuristic method, reference 41, to map each logical qubit to a data qubit within its assigned QPU. Here I provide an example to illustrate the placement process. So we can consider the quantum circuit in figure A and the modular quantum system in figure B. In the first iteration, the operands of gates G1, Q1, and Q3 are assigned to QPU1, as illustrated in figure C. In the second iteration, the operands of G2, Q2, and Q5 are assigned to QPU2 due to the capacity limitation of D1. And in the third iteration, the unassigned operand qubit of G3, which is Q4, is assigned to D1 based on its interactions with previously assigned qubits. And finally, the complete placement results after mapping each logical qubit to a physical qubit is obtained as shown in figure D. Then, in the routing stage, we iteratively apply two key steps in each iteration until all the gates in the logical circuit are executed. The first step is Taylor data and Taylor gate insertion, and the second one is local gate execution. Let me introduce Taylor data and Taylor gate insertion first. Here we begin by identifying all helpful operations. An operation with a then we compute the latency overhead and the benefit of each helpful operation. An operation with a non-positive latency overhead means that the delay of the operation is covered by the idle times of qubits, and thus does not increase the circuit latency. However, if a helpful operation has a positive latency overhead, means that the operation will increase the circuit latency. And the benefit of each helpful operation reflects the execution cost reduction it provides to the gates at the front. Then we insert the helpful operation with minimal latency overhead and maximal benefits. For more details like the cost functions, please refer to the section 3 of the paper. After we insert an inter-QPU operation, we iteratively insert a swap operation until no local gates remain in the front layer, where a local gate is a single qubit gate or a two qubit gate whose operand qubits reside on the same QPU. And similar to the Taylor data and Taylor gates insertion step, we first identify all the helpful swap operations. Then we compute the latency overhead and benefits of each one and select the swap with minimal latency overhead and maximal benefits for insertion. And Here, I provide an example to illustrate one iteration of routing stage. Consider a logical circuit as shown in Figure A, and a mapping as shown in Figure B. In Taylor data and Taylor gate insertion, we move Q1 from D1, from QPU1 to QPU2 by first swapping the mappings of Q1 and Q3, and then performing a Taylor data operation. In local gate execution, to execute G1, we exchange the mappings of Q2 and Q5 with a swap. Subsequently, we can execute G2 and G3 since their operand qubits are mapped to adjacent physical qubits within a QPU. And at this point, the only gate in the front layer of logical circuits, G4, is not a local gate since its operand qubits, Q4 and Q5, they are not on the same QPU. So we terminate the current local gate execution and start the next iteration of the routing stage. In the first experiment, we use a realistic modular quantum system consists of 3 Flamingo-class QPUs. Each Flamingo-class QPU contains 156 physical qubits arranged in a heavy hexagon topology, and every pair of QPUs is connected by 4 communication links. We compare our method with reference 19, which is the state-of-the-art for the end-to-end circuit compilation framework problem for modular quantum systems. And we evaluate our work by comparing 4 configurations, highlighted by the red rectangles. And also, to provide a broader comparison, we also include reference 28, whose source code is in reference 23. And compared to reference 19, our framework achieves over 70% reduction in final physical circuit latency across both benchmark sets. And the number of inserted Taylor data and Taylor gates is also reduced by 36% and 60% in the respective benchmark sets. And a similar advantage in solution quality is also observed compared to reference 28. And our framework has a higher runtime compared to reference 19 due to its more sophisticated routing strategy. However, our framework remains efficient in practice as it can compile a circuit with 900 qubits and more than 800K 2-qubit gates in under 100 seconds, as highlighted in the green rectangles. For more analysis, please refer to the section 4 of our paper. And in the second experiment, we extend the hardware setup to a system of 4 QPUs to evaluate the scalability of our approach. And the advantage of our approach over reference 19 and 28 is preserved. And in this paper, we propose an end-to-end circuit compilation framework for modular quantum systems. In the placement stage, we propose a dependency and interaction-aware assignment method to assign logical qubits that interact early in the circuits and frequently with each other to nearby QPUs in the system. In the routing stage, we optimize the insertion of inter-QPU operations and multiple intra-QPU operations to enable the execution of the gates. The selection of both inter-QPU and intra-QPU operations is based on their circuit latency overhead and their benefits to the subsequent gates. In the experiment, our approach outperforms reference 19 and 28 in terms of circuit latency overhead and number of inter-QPU operations on a modular quantum system with 3 QPUs. And this advantage is also preserved in a system with 4 QPUs. That's all for my talk. Thank you.
Thank you, Chen. questions for Xing Yao? Xing Yao, I have a question for you. In the first table with results that you showed, and you compare your work to the reference 19, I see that the runtime of your approach for the small benchmarks is around up to 2x, but when the benchmark size increases and it goes to in 5 seconds case, the overhead is 3.5x, and when we go to the 18 seconds case, the runtime overhead is 5x. Is there a scaling issue with your approach?
Or is it possible for us to discuss like online or through email?
Yes, of course.
Because I think the hole is too large, so I can't hear the voice clear.
Okay, no problem. Yes. Okay, this concludes this.